Okay, in this problem we're going to look at what happens, what is the final temperature when 2 grams of gold at 100 degrees Celsius, which is our hot object, is dropped into 25 mils of water at 30 degrees Celsius, which is our cold object. We're given the specific heat capacity of gold, 0.128 joules per gram degree C, and you should all know the specific heat capacity of water, the cold object, which is 4.184 joules per gram degree C, and we would not give you that on the problem set. Now, we have a theoretical system here, where a hypothetical system where only gold and water exist, and it's completely isolated from the rest of the universe, and so no heat is transferred outside of the gold and water. So we can say that the heat of the hot object plus the heat of the cold object in this isolated system, the heat changes, is equal to 0. So we can say that the heat of the cold is equal to minus the heat of the hot. So if this gains energy, this loses. If this loses energy, this gains. Now we also know that for a constant phase system, if I add heat, the temperature changes by the mass mc delta T, where C is the specific heat and delta T is the temperature change. So I now can come in here and I can say that the mass of the cold object times the specific heat capacity of the cold object times the temperature change of the cold object. A change is always a final state, Tf, minus an initial state, Tc. And this must equal to the negative of the mass of the hot object times the specific heat capacity of the hot object times the temperature change of the hot object, which is Tf minus Th. Now, let's take a quick look at what's happening over time here. If this is my axis of time, and this is time 0, and this is the initial hot temperature, and this is the initial cold temperature, the cold object is going to warm, the hot object is going to cool until they reach a common temperature. This is the final temperature. Now if we look at these values here, we have 25 grams of the cold object, and it has a large heat capacity, 4.184. So this system has a high heat capacitance compared to this system, which is a small mass, 2 grams, much less than 25, and a small specific heat capacity, 0.12 instead of 4.1. So this is going to have very little capacity to absorb the heat, so its temperature is going to change greatly. And what we anticipate is that the cold object is going to rise in temperature a little bit, while the hot object is going to cool in temperature substantially more. And when they reach the same temperature, this is the final temperature, Tf. Now if I come over here, Tf minus Th is a small number, is a negative number, because Tf is smaller than Th. So the negative of a negative is positive, and this all makes sense. This term, Tf minus Tc, is going to be a positive number because the final temperature is larger than the initial cold temperature. Now what I need to do is algebraically solve this for Tf. So I have Tf, and I'm going to put everything with a Tf on this side, times an mccc, and I have a Tf times a minus mhch, which when I bring it over here becomes a positive mhch. Now, everything without the Tf, I'm going to put on the other side, so I have a minus mhch times a minus Th, so that becomes a positive mhchth. And now I have over here a mccc minus Tc. When I bring it over here, it becomes positive, so it becomes an mccctc. Now I have my Tf is equal to mhchth plus mccctc. Excuse me. I'm going to bring this over here, but I'm going to line the mh and ch's above each other. So I have MHCH plus MCCC. Now I look at this, I can quickly see that the units of MH and CH will cancel, and so I have units of T in the numerator. And it's very important that you algebraically solve this before you substitute in your numbers. We can read this. We can't read the numbers. So substitute your numbers in at the last step. So now I'm going to substitute my numbers. And I have 2 grams of the hot object. It has a heat capacitance of 0.128 joules per gram degrees C. And it had initial temperature of 100 degrees C. And then I'm going to substitute for the cold object. I had 25 mils, which has a mass of 25 grams, because you should know that water has a density of 1 gram per milliliter, a specific heat capacity of 4.184 joules per gram degrees C, and the initial temperature was 30 degrees C. Now, I divide this by MHCH, which is 2 grams times 0.128 joules per gram degrees C. And I add to that MCCC, which is 25 grams times 4.184 joules per gram degrees C. And I notice that my grams cancel, my joules cancel, my grams cancel, my degrees C cancel. So my units are temperature. I now bring out the calculator, and the final temperature is 30.17 degrees C. And this makes sense because I had a lot of water, and water has a large heat capacitance. Its temperature barely rose. Where I had a little bit of metal, and it had very small capacitance, its temperature dropped substantially. And this all makes sense.